Have you ever just stopped and wondered why your favorite mug feels so perfect in your hands? Or why the chair you're sitting on is shaped exactly the way it is? Well, there's a hidden language in every single object around us, a language of design. And today, we're going to learn how to speak it.
I mean, seriously, just look around you, right now. Why is your phone shaped that way? Why does your computer mouse seem to just melt into your palm? It's not an accident, not at all. Every curve, every texture, every single button is there for a reason. It's all a choice.
And to learn this language, we're going somewhere you'd probably never expect. We managed to get our hands on a design and technology exam from a high school in Singapore. And believe it or not, the questions inside this test hold the keys to unlocking how and why everything is made. So you ready? Let's dive in.
Okay, first up, and this is the most important rule in the book, great design is never really about the thing itself. Nope, it's always about the person who's going to use it. Think about it. Every product you own started with a person and a problem. So this exam, it uses the example of a bus stop. A designer's job isn't just to design a bench. It's to solve problems for the people waiting there. Maybe an elderly person needs better back support to sit down, or maybe a little kid can't even climb onto the seat. The real solution always starts with understanding people. It starts with empathy. And that brings us to this really important word, ergonomics. It sounds kind of technical, but all it means is the science of making things fit people, instead of making people fit things. It's the reason your office chair doesn't destroy your back after an hour. It's all about comfort, efficiency, and most importantly, safety. So how do designers get inside our heads? Well, they've got a whole toolkit they use. They'll run surveys, they'll interview people, and sometimes they'll just sit back and watch how we actually use things in the real world. They even have this acronym, PIES, to break down our needs into 4 big areas: physical, intellectual, emotional, and social. It's a way deeper process than you might think. Okay, so you get the person, you get the problem. What happens next? Well, you need a plan. This is where we go from just ideas floating around in your head to the nitty-gritty of making something real. An idea is just a spark, right? To actually bring it to life, you have to turn it into a detailed blueprint. And that journey goes from super rough sketches on a napkin all the way to incredibly precise computer-generated designs. Now, designers don't just go straight from a drawing to the final product. No way. They build mock-ups first, models. This lets them actually hold it, feel it, and test everything. Does it feel right? Are the measurements correct? Is it even safe? A simple model can save a ton of time and money by catching mistakes before they become big problems. And the last step in this whole planning phase is the working drawing. This is the master plan, the ultimate instruction manual for the factory. It has every single exact dimension and detail on it, so the final product gets built exactly, and I mean exactly, how the designer imagined it. All right, we have the blueprint. Time to build. But how do you make sure your beautiful design doesn't just fall apart? This is where we get into the physics of it all, the invisible forces that every single object has to fight against every single day. Okay, so fundamentally, almost everything is either a frame or a shell. A frame structure is like a skeleton. It's made of lots of individual pieces all joined together. A shell structure gets its strength from its outer casing, just like an eggshell. It's a really simple idea, but once you know it, you'll start seeing it absolutely everywhere. Every structure out there, from a giant skyscraper to a little paper cup, is in a constant battle with invisible forces. The first one is called compression. That's a squashing or pushing force. Just think about the legs of the table holding up a stack of heavy books. Those legs are under compression. They're being squashed. And the complete opposite of compression is tension. This is a stretching or pulling force. The best example? The cables on a suspension bridge. They're being pulled apart constantly, in a state of tension. And any part of a structure that's built to handle that pull is called a tie. And that brings us to this really cool engineering challenge, the cantilever. This is just any beam that's only supported at one end. Think of a diving board or a balcony. It's literally fighting gravity, which creates this crazy combination of tension, stretching, on the top and compression, squashing, on the bottom. Making these things strong and safe is a real work of art. So how do you make structures stronger, especially at the joints where they're usually the weakest? Well, one of the most common tricks is something called a gusset plate. You've definitely seen these on bridges or big metal shelves. It's just a simple piece of metal that connects beams and spreads out the stress, making that whole connection way stronger. It's a simple fix with a huge impact.
All right, so far we've mostly talked about things that just stand still. But what about things that move? This is where design gets even more fun, because now we're diving into the world of mechanisms.
Let's start with one of the most basic machines ever, the lever. Turns out there are 3 types, and it all just depends on where you put the pivot point, or fulcrum. A pair of scissors is a first-class lever. A wheelbarrow, that's a second-class lever. And something like chopsticks or a pair of tweezers, that's a third-class lever. Simple, right?
Gears are all about controlling motion. Different types have different superpowers. Bevel gears are awesome for changing the direction of rotation by 90 degrees, like in an old-school hand drill. And a worm gear is incredible at slowing things way down while jacking up the turning force, which gives you a ton of power from a tiny motor. And then you've got cams. A cam is basically just a funky, weirdly shaped wheel. As it spins, another part called a follower traces its edge. This turns a simple spinning motion into a really specific, custom up and down or back and forth movement. Cams are the secret ingredient in everything from wind-up toys to the engine in your car.
All right, for the last step, let's add a little bit of intelligence. I mean, modern design isn't just about wood and metal anymore. It's often about simple electronics that let objects sense the world and respond to it.
And the exam gives us the perfect example, a simple little nightlight. How does it see darkness? Well, first, there's an input. It gets dark. Then, a tiny sensor, a light-dependent resistor, senses that change. When it's dark, it sends a signal to a tiny electronic switch, called a transistor. That switch then flips on, and for the output, it completes the circuit and turns on the light. It's just a simple chain reaction: input, sensing, process, output. So clever. So here's the big takeaway. The world around you is basically a library filled with thousands of design decisions. And now that you know some of the basic grammar of this hidden language, from why things feel the way they do to how they move and even think, I've got one question for you. Just look around the room. What's one object you will never, ever see the same way again?